Welcome back. This is session 7, part 3. Before I start the third part, I want to refresh your memory about what we have discussed in the past. We do have a tree-like structure, where attributes are actually going to branch out to different decision points, and eventually we are going to have the termination point at the end. In this example, where we have been discussing age and a student or not, as well as credit rating, we have used a number of approaches in our decision tree techniques. And if I may refresh your memory, we did use probability. And in our case, when we spoke of probability, we took the sample, the small sample of whatever the decision point is going to be versus the larger sample behind. Several examples included, such as this, included basically, for example, 2 out of 5, 3 out of 5, and then 5 out of 14. 3 out of 5, 2 out of 5, and 5 out of 14. So this is 3 out of 5, and this is 5 out of 14. This is 2 out of 5, and this is 5 out of 14. This is 4 out of 4, for example, and 4 out of 14. 14 being the whole solution sample. Solution space. So that's what we discussed in the past. Now, what we want to do, this is part 3. In part 3, again, if you review the part 2, you will see a kind of a similarity that we are going to inject into Bayesian classifier and Bayesian theorem. With that in mind, let me go back to my example. Once again, what happened was that you did have a kind of a tree-like structure coming from one attribute to another. And I just showed you that in a number of cases, what happens is that when you want to calculate the probability, you calculate the probability in a chain format. So you're going to say 2 out of 5, and then 5 out of 14, for an example, in the example I just showed you. So it is kind of a chain. So we are going to call this in a moment, we are going to call this conditional probability. The way we are going to move slowly toward Bayesian technique is that I want you to imagine that this tree-like structure is actually rotating 90 degrees and counterclockwise, and I want you to put it onto the floor. So take a look at this one. If you take a look at this one, what do you see? We do have a root node, for example, and then we have A and A bar, obviously. So you're going to say either it is going to be, for example, age more than 40 years old, or age less than 40 years old. So less than or equal to 40 years old. So if you take a look at that, if you closely examine the decision tree structure, we are talking about basically the event and whatever is not the event. So not event, so this is not event, and then that's the event. And then this is going to be inside that event. You're going to basically look at B and not B. Inside not A, we didn't see it as a not A in the past. We simply looked at its neighbor state or attribute. So in not A, we will be looking again at B and B bar. So the Bayesian theory that I'm going to, the Bayesian tree that I'm going to establish is very similar to decision tree, with some minor adjustment to the perception we are going to have. It's really related to the decision tree in general. Now, if you take a look at the B event could potentially be the B when A is happening, or the B when A bar or not A is happening. Sometimes it is noted in literature as A bar. So the total B happening in my solution space, my complete sets that I have, is going to be B when A happens, B when not A happens. So that would be the B numbers. For not B, of course, it's going to be not B A, and it's going to be not B not A. So we understand that. Now, the way we are going to actually talk about this branch, we are going to talk about this branch as in probability. So when we get to this area, so we are not talking about all of the B's. We are not talking about this B and this B all together. We are talking about one B at a time, and then we will be adding them together to get the B. So I need you to pay very close attention to this structure. Very simple to follow. You don't have to memorize anything. You just have to follow the result and see what happens. So if I wanted to see what is the probability of this outcome, and this outcome is part of the whole of the B. What's the probability of this outcome? It's going to be the probability of B once A is happening times the probability of A. Because obviously the probability of A is not equal to 1. If the probability of A was equal to 1, then I would have said the probability of B once A is happening, and A being always happening, and that would be nice, right? So in that case, because A itself is actually not going to be equal to 1, the probability, we need to actually integrate that in our own calculation. And that's what similarly we did in decision tree. If I wanted to say not B and A, I would say the probability of not B once A is happening times the probability of A. It's very easy to actually go through this tree-like structures and see the probability that are going to be stationing themselves at the endpoint. That would be the endpoint. Now, if you take a look at this, if I wanted to ask you to tell me what's the probability of B in this solution space, it's very easy. You're going to say probability of A, probability of B once A is happening times the probability of A. So that was this one plus this one, this pathway. It's going to be probability of B once not A is happening times the probability of not A. So as soon as you write or draw this tree-like structure, you position it horizontally, you look at it from the beginning to the very end, you could potentially tell me what the combinations are going to be. So if I ask you, what's the probability of not B happening, you simply need to add this probability that you're going to calculate here and here, okay? So let's continue. I want to repeat this a number of times so that you could potentially basically see the easy and simple picture. Once again, as you can see, and this is a different diagram, I just wanted to bring this to your attention. It could be B as my primary attributes. If you remember, we were just discussing whether age is going to be the primary attributes, whether it's going to be credit rating going to be the primary attribute or not. You could potentially decide the other way around. You could potentially go back and say, I want B to be my primary attribute. So there are B happening and there are not B happening. Or as you can see in this figure, sometimes they say B prime, sometimes they say B bar, sometimes they say not B. So they are the same. Now I'm going to weigh A against B. So A happening when B is happening, A happening when not B is happening. So if I wanted to calculate the probability here, what would that be, the probability here? Keep in mind the B and not B together will be the solution space, obviously. That makes sense. They are basically adding up to the entire solution space. Now, if I wanted to calculate the probability here, what would I say? I'm going to say the probability of A once B is happening versus the probability of B in the entire solution space. So that would be a multiplication here. And if I wanted to calculate, once again, another component of A that is happening, I'm going to say A once not B is happening times P of not B happening. And these two together will be my PA. So you could potentially look at it in any way. Now, take a look at this, and I'm going to discuss this sign, which is the common part, in a moment. So if you have 60% and 40%, keep in mind that this summation is supposed to be 1, right? This summation is supposed to be 1. Now, I could potentially branch out to an event called B and B bar, and this summation needs to be 1, 2%, 98%. And the same here, B and B bar, when F is happening, this summation needs to be 1. Very clear. Now, if I multiply 2 and 60, I'm going to get 1.2%. If I multiply 1 and 40, I'm going to get 0.4%. Make sense? So these two, if I add them 1.2 and 0.4, then it's going to be 1.6. That's how we are going to do it, right? So with that in mind, the idea would be this tree-like structure. Let's take a look and continue. I intentionally try to provide a number of examples to see how simple this is and how easy it can add to our perception and understanding of the exercise. So suppose you have 100,000 people and you're testing them against COVID-19. We are testing them against this disease. 1,000th of them, which would be 100, are going to show that they have the disease. And 999 over 1,000 of this, which would be 99,900, don't have the disease. Suppose that this is the whole solution space that you're looking at. So obviously, if I add 100 and 99,900, I'm going to come up with 100,000. That makes sense, right? And then if they have the disease, and it happens so, again, this is just an example. I didn't mean this to reflect necessarily COVID-19. I'm just saying any disease in this case. In my example, in my exercise, in my experiment, 100 of them have been testing positive. Well, you might argue that some of the COVID-19 people may not even test positive. But let's assume that for the time being. 100% of all of those 100 people are going to show that they are test positive. On the other hand, from 99,900, 5 of them are going to actually show test positive while they don't have the disease. So if I ask you how many people are going to have test positive, what would you say? You're going to say 100 test positive, rightly so, from this branch, this pathway, and then 4,099.5 from this pathway. You might, and these two are going to add up to 5,095. You might say, wow, this is too big. You are right. Compared to 100, this is too big. But this is versus the large segment of the sample, 99,900. Now, this is the good news, that when we have 100 and 4,995, when you add them up, that would be 5,095. Only 100 of them, of these two test positive, are actually are going to have the disease. So that's the way your brain needs to actually move around this basically tree-like structure. Once again, you may have a population, randomly selected patient, or even population, doesn't matter. You have the healthy conclusion or a sickness conclusion. 99% of the time, the person you pick up on the street is going to be a healthy person. And even with today's rates of COVID-19, while it is very important for us to be conscious and take all of the precautions to be safe, but generally speaking, the ratio compared to the entire population in US may be basically telling of how widespread it is. And then the sick people, sicknesses is going to be only 1%. Then we are going to take them, this is going to be a kind of a different types of a test, different types of a illness we are talking about. And then we are going to take them and test them, and we see that they are going to do positive, meaning that they have shown positive, basically illness. They recorded as healthy, but they have shown illness in the test results, and 90% of them test negative. And similarly, if you have a sickness in an individual, illness in an individual, 90% of them are going to test positive, and 10% of them are going to test negative. So if you take a look at my path probability, as it is said, it's going to be 0.1 times 0.99. It's going to be 0.099. 0.9 times 0.01 is going to be 0.009. These two together are going to be my test positive. And then what should you worry about and you should consider as well is that this one, which is 0.009, out of this entire set is going to be those who have been who have shown to test positive and to be ill at the same time. So this tree structure is actually quite simple to follow, okay? Once again, you can talk about cancer. These are different examples I found. And usually the probability is written on the branch instead of here. And then you can potentially go and multiply and say test positive, no cancer, test negative, no cancer, test positive and cancer, test negative and cancer. And then you can potentially add 0.93 and 0.01 as the outcome for positive test results. And then you could talk about the ratio. In order for us to understand what the Bayesian theorem is or technique is going to be, I want to draw your attention to this whole solution space. This is my whole solution space. This is my entire sample, Again, this is a pictorial way. It is called Venn diagram, and it is helping us to see what is happening in general when we talk about Bayesian theorem. After we demystify that, I'm going to go and give you a full example in a moment. Now, A is an event, and you could have B, you could have C, and let's stick to only two events in this example. A is this much of the solution space. So if I ask you what's the probability of A in the sample, well, it's a sample probability, right? So what is happening is that it's going to be the area of A versus the total solution space. That's going to be the probability of A. When I ask you what's the probability of B, it's simple. The solution, the area dedicated to B divided by the entire solution space. I hope you're on the same page. Now, when you combine them, when you put them, if you take a look at them, there are going to be some cases where this is going to be common area. We call this common area. So the common area, as you can see grayed out in this section, is going to be a smaller portion of it. So if I ask you what's the probability of the common area, what would you say? It's going to be this common area divided by the whole solution space. When I say that I want you to give me total incidences, meaning A and B together, if we say that, so it's going to be the area that you see, so the combined area divided by the whole solution space. So this is common, and we call this and this we call this or. Or means together, all of that together, and means the commonalities, the common areas that between the two circles. We did this in mind. Once again, this is another nice one. So you have an A green space versus the whole solution space, which is going to be the white space. And then you have the kind of a light blue, if I may, maybe a little bit grayish. And this one is going to be versus the whole solution space. And if I ask you to tell me what's the and area, the common area, you need to find this probability in terms of pictures and area. It would be this area divided by the whole of the solution space, okay? I want to actually alert you to this picture and make you more conscious about the notations. So once again, this is an elliptic. As you can see, this elliptic is a large one. And we are going to call this A, the A event. And if I wanted to calculate the probability of the A event, it's going to be the whole of this elliptic divided by the whole of the solution space. Let's take a look at the blue one. The blue one is going to be indicative of the event B. So that's blue one divided by the whole of the solution space. If I tell you what the common area, what the and is going to be, This is going to be the and. So there is a kind of a brownish behind and a bluish at the front. And this is going to be the part we are talking about. And if I ask you what's the probability of A and B, you're going to say, okay, let's calculate this area and then divide it by the whole of the solution space. The reason I wanted you to be alert toward this picture, because I might as well be conscious about other areas that we may discuss and point to in the future. For example, what is this blue part? Part of the elliptics that is confined in this area. What's this blue part? It's going to be not A and B. Not A means I don't want A to be involved at all. Anything not A. And B, of course, everything here. So it's going to be not A and B, or A bar and B, or A prime and B. So it's going to be reflective of this area. One more time. If you take a look at this whole elliptic and you take away this chunk, that is going to be the area that has B personality inside. Remember, this has a kind of a bluish inside. If you remember this B personality from this side, you're going to be left with pure brownish kind of a dot lines. So it's going to be A, of course it is A, but and B bar, B prime, not B, which means nothing B. I don't want to have any of the B in my segment. So what's the probability of this? It's going to be the probability of the confined space between this elliptic and the edges are going to be here. Now, one more time. If you exclude A personality completely and B personality completely, you're going to be left with everything outside of these two samples. So it's going to be A bar and B bar, A prime and B prime, or not A and not B. So that would be this area. If I ask you, what's the probability of not A and not B, you're going to look at the white area divided by the whole of the solution space, which includes everything in between. We excluded anyway, the whole of the solution space, okay? Here is the Bayesian Theorem. Now we are at the moment of truth. It's really simple to understand what this one means. This one says that this common part, A and B, is the same whether you look it from the B circle or you look it from the A circle. True, right? This area doesn't change because you're looking at B front or you're looking from A front. This area is the same. This area is going to be fixed, right? Makes sense? So, so what do we do? And now, if I wanted to calculate B and A, so from the B front, what is the probability of B? The probability of B is going to be the whole of the circle divided by the whole of the solution space. That's the probability we have. And then the event A happening once B has happened. The event A happening once B has happened. So what happens? I need to find the probability of A once B is happening. So this is A once B is happening. Okay. So in these two, when I multiply them, I'm going to get the and part of B and A. Now, if I apply the same approach and I take a look at the view from the A side, so from the A side, the probability of the A is going to be the whole of the circle divided by the whole of the solution space. And then B once A has happened, B once A has happened, so keep that in mind. That's going to be my probability. What this one is saying is that whether you say B and A or A and B, they are the same. And that's true. You can visually inspect that and confirm that, right? Now, therefore, when we substitute, what do we get? We are going to actually equate the two right-hand sides. We are going to get PA while B is happening, conditional, times PB is equal to B while A is happening times PA. So this is going to be my Bayesian theorem. And then the Bayesian theorem says that you can potentially grab anything you like from this equation. That's a true equation. And if I put A while B is happening, all I have to do is to calculate this right-hand side and divide it by PB. And remember the PB. The PB was supposed to be the B of A and the B of not A. Remember that two pathways to get us to the P of B. This is usually called posterior probability, is equal to the likelihood times the prior, and then it's going to be the whole of the evidence that we have in our case. So this is a very nice, simple way of looking at the Bayesian theorem. Let's take a look at this once more. It says that A once B has happened is equal to the common part divided by PB. So very simple. What did we do? I'm actually going to replace this with basically this one, right? So if you take a look at this, what does it mean? It means tell me about this area divided by PB. So this area divided by PB is going to give me the probability of A happening once B has happened, because they are the same, right? So that's the way we are going to say it. Take a look at this example pictorially, and then we are going to go back to our own tree in a moment, I believe. So I have these sets of people who are happy all the time. And I have these sets of people who are positive all the time. And happy people are going to be part of the larger, solution space. And the positive domain is going to be part of the larger solution space. Make sense? Now, and then we have an area called being positive and happy at the same time. Being positive and happy. Yeah, there are people who are positive, but they are not happy. That makes sense. And there are people who are happy and they are not positive. They could be happy, but they are not necessarily positive, right? All kinds of people could exist on this planet Earth. So what is this one says? It says the probability of finding a person to be positive among the sample of being happy is equal to be positive, happy together divided by happy. So it's going to be this one divided by the whole of this. Okay, makes sense? So that's going to be, so this is actually conditional probability. Okay. Now, if you understood what the approach to graphic representation of the Bayesian theorem is, you could potentially extend this if you wanted to even more kind of more attributes. So you have A and B and C. So this is going to be A, this is going to be B, and this is going to be C, right? So A and C, I have this common area. Keep in mind, this whole thing is A and C. B and C is going to be this whole area. That's B and C. B and A is going to be this whole area. And then if I say what is A and B and C, that's going to be this area. If we understood what's the probability is, we could easily say, what's the probability of, what's the probability that A has happened and I have B and C at the same time. A has happened and B and C at the same time. That's the conditional probability. What do? I could potentially calculate that in respect to C, in respect to B, a very nice exercise at home. It's really that simple. This is called a bit, take a look at this. Really, when we are talking about the two circle versus the three circle, the two circle is talking about this. The three circle is going to be having common areas, but of course you are going to have the common areas, all of the three at the same time, okay? One more time, let's go back to the health case. Remember that in the health case, this is actually quite common in research in the medical domain. You had the healthy individual, the sick individuals, you had tested positive while healthy, so that's the status. Tested negative while healthy, tested positive while sick, tested negative while sick, and then I've got this. So what does that mean? This one means healthy and positive. This one means healthy and negative. This one means sick and positive. This one means sick and negative. So I hope this, this structure is going to help us to understand what we are talking about. Now, as we said again, sometime instead of the sign that is kind of a inverse V, I would say, is they put it in a comma. Again, book to book, page to page, they have different convention, but the one that is actually this shape is I would say the standard. So again, once again, these two are the same, the right hand side are the same, and you can extract anything you want from the other side. And this is going to be, again, a conditional probability formula, and this is going to play a significant part in the Bayesian theorem. Once again, you can see A, not B, not A and B, and A and B, right? And then you can see that the formula is the same. Now, I want to alert you about this one. What happened to the denominator? What happened to the denominator? I think in this example, we had P of B, and then in this example, I have expanded P of B. What happened? Now, do you remember when we talked about this, I said that when I want you to calculate the B as the entire B from the solution space, you need to tell me this pathway and this pathway. Or if you have anything else, and in this case doesn't happen to be, you have to count them all. So whatever here is, that's going to be probability A, B while A is happening, conditional A, probability A, not A, B while not A is happening. And that's where we are going to have at the bottom of the denominator. So this is very important. With that in mind, let's see if I have, this is another nice discussion that I would like to bring to your attention, if you don't mind. This is very good, very good, nice representation of the entire discussion. You could potentially say, I'm going to start from the A attribute and then branch out on B attributes, okay? So A is happening, you have the probability of A here, and then B happening once A happened, B bar happening once A happened. So this is going to give me A and B, and this is going to give me A and B bar. And there is a B bar on top that is not much visible. Now, the complementary side of the tree we have been talking about is going to be A bar, B once A bar has happened. That's going to get me A bar and B. B bar, once A bar has happened, that's going to get me A bar and B bar. Okay, there is a bar on top that is not much visible. So this tree is actually meant this tree is meant to show that if we start from A attribute and then go through B attribute next, what is going to be the probability? Now, if you take a look at the picture at the bottom, it's a very interesting observation. What does it say? It says, let's begin from attribute B in this time, and then have A next, and then calculate. What the Bayesian theorem says is that B and A is the same as A and B. So this pathway supposed to have the same probability as this pathway. That's what Bayesian theorem says. Now, if you say, I am missing this data, it's very easy. Multiply this 2 divided by this. If you say, I'm missing this data, once again, let's just play a bit of a game here. If you say, I'm missing this data, what would you do? Find a similar branch or pathway, this one, multiply, divided by this. If you say, I'm missing this pathway, this component, what would you do? Take a look at the similar pathway, multiply this, divided by this. And that's going to be the way you're going to conclude the case. You can play with this pictorial approach to this. If you have the whole solution space, B1 as an event, B2 as an event, B3 as an event, B4 as an event, you could potentially have another event that is going to have intersection with all of this, and you should be able to easily go and apply the Bayesian theorem. So all in all, instead of this picture, we have referred to indecision tree. We are actually referring to this picture in this lecture series. Okay. With that in mind, I want to stop, And I'm going to basically give you a full example of how this has been calculated. Thank you. Stay tuned.